Nuclear theory explains reactions that happen inside atomic nuclei. Such reactions usually release energy and change the structure of matter itself. We learn about nuclear theory because there's so much more to it than just protons and neutrons. Nuclear theory explains radioactivity, and radioactive substances are essential to industry and medicine. It also explains nuclear fission, which is the source of energy for all nuclear power plants currently in use. Finally, it explains nuclear fusion, which has only one use today: the weapons of mass destruction maintained by nations in such numbers that many people believe our civilization is now at risk. But before we make judgments about the policies of our nation or other nations, it's important to have an understanding of the processes that are at the core of so much controversy. In our time, there is no greater danger than ignorance. Atoms are made up of three basic particles: protons and neutrons comprise the interior, called the nucleus. A third type of particle, electrons, orbit the nucleus at an enormous speed. The different particles that make up an atom are attracted to one another. This attraction is what holds the atom together and makes it strong. But occasionally the structure of an atom's nucleus changes. The three most common processes resulting from a change in nuclear structure are radioactivity, fission, and fusion. Most people are familiar with radioactivity because most of us have been exposed to X-rays. At this hospital cancer center, X-rays play an important role in both the diagnosis and treatment of cancer. This device takes X-ray photographs of patients who are preparing for cancer therapy. The photos are used to control the work of this laser-guided linear accelerator, which kills cancerous tumors with its powerful beam of high-energy X-rays. Both machines generate radioactivity only when it is needed. If the power is switched off, the X-rays disappear. Unlike the accelerator, naturally occurring radioactive substances are on all the time. This kind of radioactivity usually occurs in very heavy atoms. Nuclear particles escape and fly out in all directions. Most man-made and natural radiation comes from isotopes. An element with isotopes has at least two variations in the way its atomic nuclei are organized. One of them will have more neutrons. Therefore, its mass number will be larger. Even though they have different mass numbers, these isotopes are still the same substance. The only difference is that many isotopes are radioactive. When a nucleus gives off particles, the atom is actually changing from one substance to another in a process called radioactive decay. Over a period of millions of years, this isotope of uranium decays into lead. Radioactive isotopes decay at such predictable rates that we can put them to work for us. Here in New Mexico, archaeologists depend upon radioactive decay because it gives them a highly accurate clock they use to determine the age of their discoveries. Workers at this site have unearthed logs that were part of an ancient dwelling. All living things store two isotopes of carbon throughout their lives, carbon-12 and carbon-14, which is radioactive. After an organism dies, it no longer absorbs carbon-14, and the isotope begins to decay. Laboratory analysis of the logs can determine the amount of carbon-14 left in the sample, and therefore, when the logs were originally cut. The results of these tests indicate they were cut at about 1100 AD, plus or minus 70 years. The yardstick scientists use to measure radioactive decay is called a half-life. An isotope's half-life is the time it takes for 1/2 of its atoms to decay. Carbon-14's half-life is relatively short. But other isotopes with longer half-lives are used to date discoveries as old as 50 million years, and are used regularly to date the remains of the ancient ancestors of our human species. We should never forget that some radioactive substances can be dangerous. In late 1983, a man delivered a load of scrap steel to a junkyard in northern Mexico, for which he was paid about $10. Some of the junk had come from a hospital storage room. Workers at the yard discovered a small stainless steel container in the load from the hospital. It didn't appear to have much value, so they tossed it aside. The container was filled with tiny metal pellets, which spilled out and spread throughout the junkyard. Later, scrap steel from the yard was melted down at several Mexican foundries and reformed into table legs, steel ingots, and girders. These products were shipped throughout Mexico and as far north as Chicago before it was discovered that all 4,000 metric tons of steel had been contaminated by radioactive cobalt-60. The pellets were the radioactive core from a 20-year-old cancer therapy machine. 30 pellets emitted enough radiation to kill a man. But thanks to sensitive radiation detection equipment in the United States, the accident was discovered before anyone outside the area was harmed. Yet this incident shows how vulnerable we can be to the inadvertent release of radioactive materials. Nuclear fission is commonly known as splitting the atom. More accurately, fission splits larger nuclei into smaller ones. After fission has taken place, the total mass of the pieces is less than the original nucleus. Some matter has been converted into energy, as predicted by Albert Einstein's famous equation, E equals mc squared. This energy is mostly heat, generated when neutrons and other reaction products come near other atoms. The heat is very intense, as evidenced by the charred remains of the Japanese cities Hiroshima and Nagasaki after World War II. The atomic bombs detonated over these cities used nuclear fission. The fission process usually starts with atoms of uranium. If a slow-moving neutron comes near, it may be drawn into the nucleus of the atom. This causes the nucleus to split, releasing energy and at least 2 more neutrons. These free neutrons move so fast, they're able to pass through atoms. But a material called a moderator can slow them down enough so they can cause other atoms to fission, releasing energy and more neutrons. The reaction will be set in motion. The reaction continues at blinding speed, and if left uncontrolled, results in a tremendous blast of heat and other radiation. is very difficult to make a fission bomb. It is far easier to control the reaction and release the energy very slowly. A nuclear power plant uses fission to produce energy, but can never become a bomb for many reasons. The reaction in a nuclear power plant is regulated by a special material, control rods, that absorb some of the neutrons set free by the reaction. So the reaction continues, producing heat and driving electrical generators. But an uncontrolled chain reaction is prevented. In the 1950s and 60s, the United States took the lead in developing fission-powered electrical generating plants. At first, these plants were well received because they didn't pollute the air, and many people hoped they would produce electricity so inexpensively that it could be offered for free. On March 28, 1979, public opinion began to change. Shortly after 4 a.m., Unit Number 2 of the nuclear power generating plant on 3 Mile Island began to experience an unprecedented series of mechanical failures and human errors that took the reactor close to a meltdown. A meltdown results when a reactor's cooling system fails. The uncooled reactor core melts into a 2,900-degree mass of radioactive mud that cuts its way through the plant and into the earth below. No reactor has ever melted down anywhere in the world, but if one did, it would probably threaten the lives of people living nearby. The possibility of a meltdown at 3 Mile Island was over long before anyone knew there was a problem. In fact, 3 Mile Island may never have endangered human lives. But we really don't know. However, there was plenty of blame to be spread around after the accident. Federal officials who overlooked reactor design flaws, poorly trained technicians, and journalists who irresponsibly fed the tide of fear that swept the nation. This single event damaged the reputation of the nuclear industry and caused many people to question whether we're mature enough to control such an awesome force. Nuclear fusion provides another method for releasing energy by changing the structure of atomic nuclei. At its simplest level, nuclear fusion is the joining together of hydrogen isotopes to create a single atom of helium. Before fusion can occur, the hydrogen atoms must be heated to a temperature near 100 million degrees Celsius. At this extreme temperature, the hydrogen atoms become unstable, and their electrons are no longer held in orbit. Nuclei like these, stripped of their electrons, are called a plasma. The heat makes the nuclei very energetic, causing them to fuse together into a single nucleus. The reaction releases energy, mostly heat, which is intense enough to cause other nuclei to fuse. The result can be a 100 million degree fireball, against which there is little, if any, protection. A fusion reaction out of control results in a thermonuclear bomb, commonly known as a hydrogen bomb. Scientists who wish to control fusion must cope with its enormous heat. Also, plasma is a very difficult substance to work with. Some researchers are surrounding plasmas with a strong positive magnetic field. Since free nuclei are also positively charged, the magnets will confine them, even at fusion temperatures. They hope to use this technology as a cornerstone for a fusion reactor that will generate electricity. Another difficult problem is getting the temperature high enough for fusion to start. Once underway, the reaction creates its own heat. Scientists at Lawrence Livermore National Laboratory are experimenting with one possible solution. the world's most powerful laser, which when completed will be used to ignite microscopic particles of fusion fuel. The problems confronting scientists today are immense, and there is little hope of having a working fusion reactor completed in this century. Such reactors could offer great benefits, especially since the only fuel they'll need is seawater. But they might also present a significant radiation hazard. It will be years before we have all the answers. Even without fusion reactors, nuclear fusion as the driving force behind the world's arsenal of nuclear weapons has become a major source of fear and controversy. Many people think these weapons serve a useful purpose and actually prevent war. They believe that nations will be so afraid of the possible effects of a nuclear war, they'll avoid any war at all costs. This theory is called deterrence, or MAD, for mutual assured destruction. Opponents of deterrence view the mere possession of nuclear weapons as an invitation to use them. They fear that temptation and greed will win out over good sense. In recent years, a new weapons strategy has evolved that promises to generate at least as much controversy as deterrence. This is the so-called Star Wars defense. Proponents of these weapons want to build defensive missiles and satellites that could destroy an enemy's missiles long before any nuclear warheads are released.
If we manage to show that shields are more effective than swords, then both sides are apt to get more shields, and that will contribute to stability.
Dr. Edward Teller, physicist, worked on the original atomic and hydrogen bomb projects in the United States. Currently, he is Director Emeritus of Lawrence Livermore National Laboratory in California.
I feel very strongly that the way to preserve peace is not deterrence by mutual assured destruction, but deterrence by establishing as good defenses as we ever can, and these defenses are beginning to look really good. Strangely enough, the people who opposed the hydrogen bomb because it was too terrible now oppose the defensive weapons because they are not terrible enough. Because they may seem to make a nuclear war less dreadful and therefore make it more probable. I don't think they can have it both ways. I also know that we must go ahead with the defense that the Soviets are already practicing, that we must remain in the lead in technology.
A lot has been said about defending ourselves against missiles, protecting ourselves, but this is not a way out of the armaments race.
Dr. Victor Weisskopf, physicist, also worked on the first atomic bomb. Today, he is Professor Emeritus of Physics at Massachusetts Institute of Technology and a member of the Vatican's Committee on Nuclear Weapons.
First of all, we cannot defend ourselves 100%, and even if 10 or 5% go through, we are all ruined. Second, it will not end the armaments race because the other side will only increase its nuclear missiles and will introduce countermeasures against defense, which are very easy and usually cheaper than the defense itself. The only way to avoid this catastrophe is to have a new attitude. We must recognize that it is impossible to change the Soviet regime by force or by threat of force. On the other hand, it is also impossible for the Soviets to make the West communist. We must negotiate to reduce the number of nuclear weapons in a fair way. We could even start unilaterally to reduce our own strategic weapons by 10 or 20%, we would not be less safe. Finally, we must introduce an effective crisis management. We should automatically get together with the other side in case of a serious crisis, before any action is taken. At present, we are on a collision course. If we don't change our attitude, we will collide. We must start now in changing our ways. Time is running out.
Nuclear theory deals with matter and energy on a scale billions of times smaller than we can see, and at the very limit of what our best instruments can sense. Yet from it comes energy in more abundance than anyone could have dreamed less than a century ago. The energy brings with it a responsibility. We must be informed and involved.
One trouble is that our people are not sufficiently informed. The scientists are perhaps more than willing to talk, but we have much too much secrecy. Today, in the atomic world, a democracy will not survive without adequate information.
It is important to learn enough about the issues to be able to agree or disagree with political leaders, and to make our opinions known through the ballot box. For when we tap the nucleus of an atom, we unleash the most potent forces in the universe. And we must prove ourselves equal to the task of dealing with them intelligently.